So in this section, this is a pretty dense section. There's a lot of different ideas that we're going to be talking about in terms of continuity, some of which are kind of just straightforward vocabulary, some of which we really just need to take some time to dive into the concept and play around with the ideas. And this first concept is just, what does it mean when we say something is a function is continuous? It needs some work. So you've probably been taught in your algebra classes that when we say a function is continuous, it means that we can graph it without picking up a pencil. And that's a pretty good definition, but it's not a great definition because it's more of a description than a definition. It's telling you what it'll look like, but not why you can graph it without picking up your pencil. So because of the graph of a function is actually an infinite number of points, we're going to step back from talking about a continuous function, and let's just talk about what does it mean if we say that a function is continuous at one point. Because if we can say it's continuous at one point, we can then expand that to all of the points. So the way we're going to do this is we're going to look at three things. For a function to be continuous at a point, the function needs to exist there. In other words, I can't have a hole in the graph or a vertical asymptote. There has to be a function value for that x. Then the two-sided limit needs to exist. And I'm going to be kind of loose with this part because if we're at an endpoint, two-sided limits never exist at an endpoint of a function because of domain restrictions. So if we're at the endpoint, instead of two-sided limit, we're looking at the appropriate one-sided limit. So if you're at the right endpoint, you're saying the left-hand limit exists. If you're at the left endpoint, you're saying the right-hand limit exists. And then the function and the two-sided limit need to equal each other. Broadly speaking, the first point there, this is saying that my function exists at that point. This is saying, what is my function approaching? And this part says that what the function is approaching is the same as what it is. In more symbolic fashion, if I want to show that some function f of x is continuous at a specific x value of a, we have to show f of a exists. In other words, just plug a into the function and make sure we get a real value. Find the two-sided limit of that function and show that that's a real value, and then show that the two-sided limit and the function at a have the same value. If any one of these fail, we can stop and say the function is discontinuous at that value. So if f of a doesn't exist, I don't even bother looking at the other two things. I already know the function is discontinuous. So then, examples of this. I'm going to spend a lot of time dealing with piecewise functions because that tends to be how the AP exam approaches it. But it's also just there are common issues when it comes to piecewise functions. So I have this function g of t where t squared is going to look like t squared when t is less than 1 and t minus 2 when t is greater than or equal to 1. And I want to decide, is this continuous at t equals 1? And I could graph this because our calculators can graph piecewise functions, but I have to be able to explain why the function is continuous or not. And that goes back to the three things I have to show. So the first thing I'm going to do is I'm going to see if my function g exists when I plug 1 in for t. So if t is equal to 1, that means I use the second piece. So I have 1 minus 2. That's negative 1. So that's good so far. I get a value for g of 1. Next, I need the two-sided limit as t approaches 1 of g of t. Well, for a two-sided limit to exist, the left and right-hand limits need to be the same. So I need to really look and see what's the left-hand limit as t approaches 1 from the left side for g, and the limit as t approaches 1 from the right side for g of t. I'm going to focus on the left side first. So if I'm approaching from the left, my t values are smaller than 1. So since the t values are smaller than 1, I'm using the piece t squared. And I can now just plug 1 in and use substitution, and that's 1. Well, already I see an issue. I can see that at best, my two-sided limit is going to be 1, which is not the same as g of 1. I can actually stop here and say, no, g of t is not continuous at t equals 1, because my left-hand limit's not going to equal g of 1. And if the left-hand limit doesn't equal that, the two-sided limit doesn't equal it. I'm going to go ahead and show the rest of the work just to show all of this, but I actually don't need to do all of this now. So if I go to my right-sided limit as t is approaching 1 from the right, that means t is bigger than 1, so I would use the t minus 2 piece. Whoops, my apologies. I can do substitution and I get -1. And what I actually can now see is from this, the two-sided limit as t approaches 1 of g of t does not exist. So if I'm asked, how do you know that g of t is not continuous at t equals 1? I can say because the limit as t approaches 1 from the left of g and is not equal to the limit as t approaches 1 from the right for g, causing my two-sided limit to not exist, so the function is not continuous. Slightly different example is I have this function, also piecewise, h of s, where as long as, oops, these should be s's, not t's. I apologize for my typo. So when s is smaller than 1, it looks like s squared. When s is greater than or equal to 1, it's s. Well, I still do the same three things. First, I want to see, does h of 1 exist? So if s is equal to 1, I use the second piece, and I get 1. That's good. So h of 1 does exist. I move on to, does the two-sided limit exist? Well, for the two-sided limit to exist, the left and right-hand limits need to be the same. So I need to find the left and right-hand limits as s is approaching 1 from each side. If I focus on the left-hand limit first, since s is approaching 1 from the left, that means s is smaller than 1, so I would use the first piece. I do substitution, and I get 1. That's looking good, because that's the same as h of 1. So now I'm hoping I get the same thing when I do the limit as s approaches 1 from the right. Well, if s is approaching 1 from the right, s is bigger than 1, so I use the second piece. I can do substitution, and I get 1. So this means that my two-sided limit as s approaches 1 for h of s is equal to 1. And now, since h of 1 is equal to 1, which is also equal to the limit as s approaches 1 of h of s, h is continuous at the point s equals 1.